Hello, this is Mr. Harris with the circles conic section. I'm going to start with circles. It's the first one. It's also the intro to conic sections. Look at this, two cones inverted on top of each other. I'm going to share screen. Here we go. Okay, there's lots of theories about the shape of, say, our entire universe. One of those theories is that there are two inverted conic sections, complete cones, conic cone, all that good stuff. Whatever's going on here, whatever's going on here, there's a black hole at the center of every galaxy. So there's a theory that there's a black hole somewhere at the center of the universe. Simply patterns sort of exist, stages exist on larger or smaller scales. Hint and shout out to, remember that unit when we did sequences and series and we did fractals, chaos and fractals, same iterated pattern over and over again. There's also a theory about what's going on in black holes, theorizing. Let's say this is an event horizon. Whatever's going on here, theory that it's a portal someplace else, somewhere else, fifth dimension, 10th dimension, whatever it is. But generally, conic sections, let's say we have two inverted cones. Let's say we have a giant sword and we're slicing through. Let's start with the circle. If we're slicing through this cone, completely perpendicular to the ground, completely parallel to the ground. Slicing through the cone completely parallel to the ground, we get a perfect circle. If we're slightly off, slightly askew, we get an ellipse. The ellipse is the proper term, not an oval, ellipse. If we completely slice through here, we get a hyperbolic function, hyperbola. It could be perpendicular to the ground. It could be slightly askew, as long as there's a parabolic shape up here that meets with another parabolic shape with some relationship between the distance apart. And then lastly, if we only slice through one of these, we get a parabola. In 2 dimensions, each of these orange planes are 2-dimensional planes, so it doesn't really matter where they are. In 3 dimensions, we would consider things on a 3rd dimension. I'm going to share another screen. We got Conics lesson 1. Hit fast forward and all that good stuff if you need. That's why fast forward exists. Here we go. Okay, here we go. Conic sections. We have the central axis, generator, all that good stuff. These are the names. I will post this. This is what would have been your problem set for this unit. However, just to make life easier on you, I'm not going to assign the problem set. And easier on me because I don't have to grade it. I'm just going to post what this would be next to these solutions. I'm going to do circles in this one. This has a nice way of going through circles and what they are. Graphing them. This is ellipses, graphing an ellipse from the equation, writing the equation of the ellipse from the graph. We have parabolas. And then hyperbolic functions I have to tackle on at the end because this source didn't have hyperbolic functions, so I wrote up my own. But let's just discuss circles. We've done circles before. Pythagorean theorem, a squared plus b squared equals c squared. Except now it's a bit more complex. This minus h, this minus k allows us to transform a circle. The origin is the dead center of the circle. In this case, radius is r squared, so the radius is 4. Um, Approximating the center, 1, 2, 3, 4. This is the center. It radiates out. A circle is a locus around a specific centralized point. Looking here, instead of it being at the origin, we moved left 1, and that's it, left 1. Looking at the equation for a circle, x plus 1 squared, remember if it's inside parentheses, we go the opposite direction. So when it's x plus 1, we move from the parent circle left 1. We don't move up or down at all. That's the equation of a circle. Here, in this example, we move a circle 3 units right and 4 units down, radius of 3. Wow, look at that. 3 units right, 4 units down, radius of 3. I would do 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Once I have 4 dots, I would connect those dots. I wouldn't want to be bothered with this radius of 3. That's just the example. For the domain, starts at 0, ends at 6. For the range, from -7 up to -1. It's so simple. So now I'm going to work through the example. Okay. So again, this right here, and again, this is posted next to it. You do not have to print it, only if you want to. This is the general form of a circle. Notice it is a parabola. We just have x squared and also y squared as well. It's not a function, technically, because it fails the function test. Remember, if it's a function, it passes the vertical line test. But we can definitely and easily write this in one way, shape, or form, where it's one variable is raised to the power of 2. But why would we do that? We learn to work without doing that. These are examples of circles. One way to tell it's circles is you look and you see an x squared and also a y squared. If just one of the variables are squared, it's more than likely a parabola. Another way to tell if it's circles is looking at the coefficients. Generally, the coefficients should be similar, the same, because circles are the squares of conic sections. A square is to a circle as a rectangle is to an ellipse. So the coefficients of the x squared and the y squared would be the same because it's the same dimensions, or you're dividing by the same term. Another thing is that you're simply adding the x squares and the y squares. Nothing but plus signs here. It's minus minus, but if I factor out a -1, it'll be -1 times this plus that. So, we can probably work with that. Again, this is the standard form, and this is the form that's very helpful in actually graphing. This helps us find the origin of the circle and the radius. So I'm going to walk you through this example 1. What I post, there's little clues off to the side if you need. I'm going to just zoom in so you can see it more easily. But there's clues off to the side to this PDF posted if you need it. But let me just work through this. And then we'll try to graph it or verify that this graph fits. We do need to complete the square for this, just like we needed to in the last section. That's why I assigned complete the square first. The thing with this, we have to complete the square for the x terms and the y terms, not just one of the terms. The best way to begin this is to simply rewrite it where the x's are with each other, x squared plus 6x. Now let's do the y terms, y squared minus 4y equals, I'm going to go ahead and subtract this 4 from both sides. Take note, the coefficients of the squared terms are 1, so there's nothing extra to do there. We don't have to divide out or factor out the coefficients. But we can, again, begin completing the square for the x terms and also complete the square for the y terms because there's 2 squared terms. Here, remember, it's b divided by 2 squared. So in this case, for the x's, it would be 6 divided by 2 squared. And here it would be -4 for the y's divided by 2 squared. So ultimately it's 3 squared. Ultimately, this is -2 squared. So let's go ahead and rewrite these terms. X squared plus 6x plus 3 squared. Those are the x values, plus y squared minus 4y plus negative 2 squared equals negative 4. And remember, I'm going to add both these terms to the other side because just like a seesaw, we have to keep it balanced. So if I added this and this, I have to add it over here. So equals negative 4 plus 3 squared is 9 plus negative 2 squared is 4. And remember, it's very helpful to keep it as this parentheses squared, if you remember from the last video. So to simplify this and write this as a perfect square, essentially to factor this, I get x plus 3 squared. And if you factor this out, you would get x squared plus 6x plus 9 plus y minus 2 squared equals 9. And that's the standard form of a circle. Looking at this, starting at the origin, we move 3 units left, and then we move, get this, 2 units up. Because same thing for y's. If it's in parentheses, we still do the opposite relative to y's, just like we would for the x's. The only time you go directly is if it's not inside parentheses squared. And if you look at the equation, we move 1, 2, 3 units left and 2 units up. The radius, 1, 2, 3. Remember, it's the square root of 9. Generally for this class and for this test, you're going to be given nice, pleasant numbers where it's perfect squares. But in the real world, let's say your radius, I don't know, let's say r squared was 24. Your radius wouldn't be a nice, clean, whole number, but you can definitely work with that. Whatever the square root of 24 is, we can work with that. It's just why bother putting you through that when we're just looking for the general consensus, if you will. So writing the center of the circle, it would be negative 3, comma, positive 2, and the radius is 3. All right, it's so simple, right? I will also be having slides posted for Conic Sections. If you work through this, it really does make a lot of sense. You're learning how to graph circles and such. On to the next page. I suggest you pause this and try to work this on your own if you can. Notice the instructions I have here. Since A and C are not 1, first divide both sides by A. I'm gonna, okay, let it, yeah. And again, we treat x squared and y squared separately. That sounds weird. We treat x squared and y squared separately but equal, but we know generally that doesn't work, except in the world of math, I guess. But they're right next to each other. We break them down and work them out. I have my 2x squared. There's no other x terms, so I'm going to go ahead on to my plus 2y squared minus 16y equals negative 4. There's several ways we can approach this to keep life simple. I'm literally going to simply divide everything by 2 only because they're both 2. When we get to ellipses, there'll be something slightly more nuanced and complicated, but stay tuned for the ellipse video, which will come after this. In this case, I'm dividing everything by 2 because it works out nicely and cleanly because they're all divisible by 2. I get x squared plus y squared minus 8y equals negative 2. I do have to complete the square for the y terms, but there's no point in completing the square for the x terms. If you notice, the circle didn't move left or right from the origin. So we'll have x squared plus y squared minus 8y, negative 8 divided by 2 squared. That would be negative 4 squared equals negative 2 plus negative 4 squared is, what's that, 16? Then we can rewrite this and complete the square. We have x squared plus y minus 4 squared equals positive 14. And this is a case where our radius squared isn't a nice clean number, but it still works out. We have calculators and such. So, and looking at this, we notice we move the parent circle up 4 units because it's inside parentheses. 1, 2, 3, 4. If you take the square root of 14, it's some number close to 3.7. 1, 2, 3, and then a smidge. Voila. So the center of the circle, I didn't give this to you. Okay. 0, 4. And the radius, the radius is the square root of 14, which is approximately 3.7. That's it. Circles, basic, to the point. I got a random call from Missouri. If only those weird, whatever you call those weird calls from people trying to hustle me into giving up my social security number ended in all of this. Oh, but people are getting tax returns and government checks, so I guess there's money to be had, so the hustlers are out there. Okay, so let's move on to lines tangent to a circle. We have the equation. Looking here, from the origin, we moved right 1, down 2. The square root of 26, whatever that is. I generally don't trust these diagonal lines. So let's just go straight out. 1, 2, 3, 4. Should be a little bit more than 5. 5 times 5 is 25, but such a smidge more than 5, it's hardly noticeable. So that's definitely the equation for this circle. They're giving us all this information. Please pause this and try to solve this on your own. It's a very good review for linear functions, especially for those of you wanting to deal with calculus next year. Remember, all we need for an equation of a line are 2 coordinates. There's also a theory that they tell us this is tangent. Because this line is tangent to the circle, it meets the circle at one unique point. It also meets it at a 90-degree angle. That's one of the wonderful things in math. It has to, in order to be tangent. Tangent means it hits the circle at one unique point. So going through all of this, I'm just going to work through this problem, try to solve it on your own. Based off of these coordinates we're given, I'm going to calculate the slope. And this is based off of the slope of the radius line. Let me label this x, y, just to keep track of where my y's are. Remember the formula for slope? 3 minus -2 divided by 2 minus 1 equals 5 over 1. So if the slope of the radius is 5 over 1, and we know the tangent line is perpendicular, we change the sign and take the reciprocal. So now we know that the slope is -1 over 5 for the tangent line, which is perpendicular to the radius. And the good thing about radii are radii all over, wherever they meet up. If it starts at the origin, ends at the end of the circle, it's the radius. Now let's calculate the equation of the tangent line with slope -1/5. We get, I'm going to use the point slope form of an equation. Remember that equation? Nice equation to have in your arsenal of mathematics. So it's going to be, and I'm going to choose this 2/3. Why not? Either point would work. Y minus 3 equals -1/5 times x minus 2. That is an equivalent equation. We can simplify if we want to. -x over 5 plus 2/5. I'm going to add 3 to both sides. Plus 3, these cancel. 3 times 5 over 5. Mr. Sneaky One strikes again. So we have y equals -x over 5. This would be 15 over 5. So I'm left with -x over 5 plus 17 over 5. Another way to rewrite this is if you don't want to divide by 5, you multiply everything by 5. So we're left with 5y equals -x plus 17. And then you can rewrite this if it's helpful. Remember, there's another way to write a linear equation. You could write it like this as well, or you can leave it like this. And that's the equation of that tangent line, and we can use that to do all sorts of things. Tangents give us the rates of change across curves, tangent lines, all that good stuff. That's it for the equation for circles. I'm going to go now work on the ellipse function. Have a good day. Take care.